Alright, so taking a look at your assignment sheet, a couple things to take note of. We're back to a normal length unit. Our last unit was pretty short, so this is our normal length here. Notice that a lot of the days do have some textbook work, so just keep that in mind as you're doing your homework. Alright, so last night you did vocab and the Unit 6 Lesson 1 notes. A lot of that was review of what you had done in, I don't know if it's elementary or middle school, but like concave, convex, what is a polygon? Some of it was new, we're going to go over that today. And then today we're learning two theorems, the polygon angle sum theorem for both interior and exterior angles. It's a pretty simple topic for today. Next class is when we get into the nitty-gritty of it. So this unit is basically we're taking a look at quadrilaterals and properties of certain quadrilaterals, how we can prove if there's certain quadrilaterals. If we know there's certain quadrilaterals, what do we know about them? So proofs do come back. I know you guys missed them last unit. And so if no snow days happen, then we're looking at our test being February 13th. Snow days happen, we'll adjust accordingly. I'm all for snow. All right. Any questions on our pacing here? What's going on with this? Okay. So let's go and take a look first at your vocab. I'm just so we have more time to go through things today. I'm not going to come around and check homework for points today, so go ahead and just put an X through that box. Vocab sheet in the Unit 1 or Lesson 1 notes. And then let's just go and start going over this. Again, you shared with your shoulder partner, and so ideally you covered any gaps you might have had. So let's talk about what we have so far. All right, so polygon, it was kind of like a paragraph for a definition. So I've included just the main things here. It's a closed plane figure. That means it's a 2D shape. It's on a plane. It's a flat surface. And it has at least 3 sides. If you think about it, you can't have 2 sides and it be closed, because then that just becomes one line. There are no curves, so the sides are segments, straight segments, and no sides cross. Now we have 2 kinds of polygons, so I'm going to skip down to that, convex and concave. A concave, you can see, oops, sorry, I flip-flopped those. I flip-flopped my pictures there. Concave, all of our vertices point out and no diagonals go outside the polygon, so I flip-flopped those guys. I apologize. Let's write this. This is convex. This is concave. Okay. Convex is the kind where there's no diagonals to go outside the polygon. Concave is where we have part of it goes in. So you'll see it says at least one vertex points inward. So this guy here. You see it's kind of like the scoop has been taken out of it. If you think of a cave, like a chunk has been taken out of the side of the mountain. So that's how I remember convex versus concave. We mainly work with convex polygons. Concave polygons don't have a whole lot of special properties. Our convex polygons do. So if it just says a polygon, it is assumed that it's convex for this unit unless it's otherwise specified. All right, and then we have a quadrilateral. That's our main focus of this unit, so it's a polygon with 4 sides. We've dealt with just triangles for the most part so far. So quadrilateral is a 4-side polygon. And then we have specific kinds of quadrilaterals. So parallelogram, rhombus, rectangle, square, and trapezoid. So these are all quadrilaterals. And we have a parallelogram, has 2 pairs of parallel sides. And subgroups of that is rhombus, rectangle, and square. These 3 are all special kinds of parallelograms that have additional properties about them. This we'll be kind of diving into next class. And then a trapezoid is not a parallelogram. So be careful of that. Because a parallelogram is defined as having 2 sets of parallel sides. And a trapezoid is defined as having only 1 set of parallel sides. All right. Before we take a look at the formulas for area, questions on the vocab that we had up there? Have we heard convex and concave before in our previous videos?
In science.
Yeah.
Really, in science? Oh,
Not in maths.
All right, so let's talk about our area formulas. You might have had a slightly different area formula, like in terms of letters that are used. Triangle, pretty much that's basic, 1/2 base times height. Rectangle is length times width. Square, you can still use length times width, or it's just your side times side or side squared. Now trapezoid, you might have seen where it said a plus b times h over 2, or 1/2 h times b1 plus b2. That's fine. The a and b represents the same thing that b sub 1 and b sub 2 is. So these are just simply the basis. So if you want to go ahead, or if you need to go and draw a picture in there, again, if you had a plus b, that's fine. It's just saying a is one of your bases, b is the other. H still represents your height. And again, there's a variety of ways this could be written: 1/2 h times b1 plus b2, or b1 plus b2 divided by 2 times h, but it's all the same thing. Add your bases, divide by 2, and multiply by 3. Rhombus, kind of a unique one here. Some formulas will say p times q divided by 2. Same idea here is d1 times d2. What that is the length of your diagonals. So d1, or p, is the length of one of your diagonals, this whole thing here. And q, or d sub 2, is the length of the other diagonal. So it's 1/2 times the product of the diagonals. And then our last thing down here, to find the sum of the angles of any polygon, this is actually what we're diving in today. So it's 180 times n minus 2. And then I just go write this note at the bottom. It's the other thing that we're learning today. Sum of the exterior angles is 360. So go ahead and add that in there just so you can kind of use your vocab as a reference sheet as we go throughout the unit. So we'll be doing some with area, not a whole lot in this unit. We have a unit later on where we do area, surface area, volume, things like that. So we'll dive more into it. Alright, and then the backside you do not have to do yet, because that's if you want to. Questions with our formulas here? Okay. So now let's take a look at the more exciting thing that you did for homework, which you learned the names of polygons. Alright, so again, this was just a couple pages in the textbook where it was recapping stuff you had probably learned beforehand. Some of it might have been new. So again, polygon is a 2D shape, it's closed. The sides are segments, so there's no curves. And the sides do not cross. So you had to identify first that these were polygons, and later on you had to decide convex versus concave. So again, it has to be a closed plane figure, which is why we got rid of that guy. And we can't have any curves. The sides should be segments, which eliminated this, and this, and this, and this. And no sides cross, which eliminated this guy. So the remaining ones were polygons. Questions on that? Okay. And then we talked about, or then you wrote about convex versus concave. So again, convex, all of our diagonals stay inside the polygon. All vertices point out. Concave, again, focus on that word cave there. At least one vertex points inward. If I were to draw all of my diagonals, at least one goes outside of my polygon. So here I just drew a few of my diagonals, but I can see that these are going to go outside of my polygon. Alright, so then a diagonal is a segment that connects two non-consecutive or non-adjacent vertices. So for example, if I start off with this vertex here, I do not go adjacent because that would just be the side, but I can connect every other vertex with it that's not adjacent. So on this first one here, I went ahead and drew in all the diagonals just to kind of give you a representation here. And we can see that for a convex polygon, all the diagonals lay inside the polygon, none of them go out. So go ahead and write this part, and you probably didn't have this in here because I added that into it. Go ahead and write this part underneath your diagonals. Maybe. Oh, there we go. Okay. Just to help you have another distinction of convex versus concave. And again, if I take a look at my diagonals, starting with my vertex here, I do not do adjacent, but but I can do every other vertex. This one's going to have a whole lot more. We can see that some of those diagonals fill out. So again, concave, at least one diagonal lies outside of the polygon. You don't have to have more than one, but at least one. So then, knowing our definitions of convex versus concave, you had to go back up and identify the ones that are polygons as either convex or concave. I'll bring that back down for you. Mark forward the buttoning. We've been struggling today. So again, identifying convex versus concave. If it has kind of a scoop taken out of it, then it's going to be concave, as we can see. This guy, a chunk taken out of it. This guy, a chunk taken out of it. Or looking at your diagonal. Diagonal lies outside of it. Lots of chunks taken out there. Questions on the front side, convex versus concave diagonals?
Can you show the diagonal that lies on side on that?
On this one here?
No, on that one.
This guy?
On that one.
Oh, I'm sorry, this one. So if I go from this vertex to this vertex here, that entire diagonal lies outside. Or I could even say from this vertex to this vertex, part of it lies outside, which would automatically indicate.
So is that little area adjacent one?
This one here. Adjacent would be the vertex directly next one, clockwise or counterclockwise. So this one's not considered adjacent. Does that make sense? Other questions on this front side? Okay. Nothing earth-shattering here. But on the back side, I think, is more fun because we have some fun names that come with it. So again, the top is pretty much review. Equilateral versus equiangular. Equilateral, all the sides are congruent. Equilateral. Equiangular, all the angles are congruent. And if it is both sides congruent and angles congruent, then we call it a regular polygon. Be careful that you do not assume a polygon is regular. Particularly in elementary school, you're usually presented with regular polygons. You're not often shown non-regular ones, so don't assume that it is regular. It must be given to you, stated, or with markings on it. So if we think of a three-sided shape, that would be a triangle. A regular triangle would be an equilateral triangle, because it's all sides and angles are congruent. A four-sided shape, so quadrilateral. A regular quadrilateral would be a square, because all the sides and the angles are congruent. And then a five-sided shape, pentagon, regular pentagon, that's probably what most of us think of. Octagon, like a stop sign, is typically a regular octagon. But again, sides and angles. Okay. Questions on that top? This is not super thrilling. Okay, so now let's take a look at the names. Feel free to name your animals after something. Call your dog Nanagon. That's not a bad idea, actually.
Your dog?
Yeah. Or your fish, whatever you feel like. Probably gonna talk to your dog before they your fish.
Why would you name your dog? It doesn't have my.
Because it's a fun name. Ooh. So is there a nine-legged animal?
You could call it a quadrilateral.
You could call it a quadrilateral. I guess you could get a spider and call it an ostrich. That sounds exciting, though. We need a 12-legged something. This is my favorite
You could
dodo.
call it drill or quad.
I like the
I like
What's
that.
up, quad?
Okay, so we have our names of our polygons here. So probably the ones you guys are not as familiar with. A seven-sided shape is a heptagon. Another word for this, you might also see septagon. So heptagon or septagon. And then 9 is a nonagon or enneagon. I rarely see enneagon. I feel like nonagon's more common. 11 is a hendecagon, and 12 is a dodecagon. I personally think dodecagon. In college track, there's actually the pentathlon, heptathlon, and decathlon. And so the pentathlon has 5 events, the heptathlon has 7 events, the decathlon has 10 events. There's also what's called the double decathlon, which is 20 events, and they do literally every single event in track over 2 days, which is pretty crazy. I mean, that's everything from like the 100 to the 10K. And you do the 5K, the 3K, and then the mile.
10K
6.2. 25 laps on that track. Yes, Teresa. Let's help with the last. Great question. So what's going on with this stuff? So once we get beyond 12 sides, I'm sure if you look at a wiki page, there's probably names for a 13-sided, 14-sided, whatnot. But once we get past 12, we call it a 13 dawn, 14 dawn, 15 dawn. So it has 96 sides and 96 dawn. So that N is just however many sides it has, that number dawn. Now you do want to be familiar with these names because on homework and assessments, if I ask you what's the interior angle of a nonagon, and you know that that's a shape. So make sure you know these names that are here. You never know, I might throw a hendecagon at you. Yes, on.
So can you have an infinite number of like sides?
Ooh, great question. So we're going to go a little theoretical with this. As your number of sides approaches infinity, your shape actually approaches a circle. So if you think about it, if you were to do like a regular polygon, so think of just like a 12-sided one, and then a 100-sided, they're going to get closer and closer. Your angles will get closer and closer to being like no longer an angle without curve there. So you cannot have infinite sides because infinity is not a tangible number. But as you approach infinite number of sides, your shape approaches a circle.
Can you show us some of that?
Someday I will get one for you.
Can you draw one?
I will not draw a 1,000-sided shape.
Can you look it up right now? Because I really want to see it right now.
Not right now, because we have things. So, sorry, on the
Can you
front.
draw us a 20-sided?
Alright, so now let's take a look at the bottom part here. Your angles, so we're talking about interior versus exterior angles. So your interior angles, angle A, angle B, angle C, angle D, angle E. For exterior, remember we just simply extend the sides. So I went ahead and, for easier labeling, so for easier labeling, I went ahead and extended the sides and labeled my exterior angles with numbers. So again, exterior angle, you just extend out the side, and this would be one of my exterior angles, and then so on and so forth around. So our exterior angles, again, we only have to do this in one direction around. So we have 5 interior, we have 5 exterior. Yes.
I don't understand what the interior angle is. Like, where are they interior to?
It's inside of your shape. So if we think back to triangles, this is when we first learned interior and exterior angles. We had the theorem that said, hey, guess what? For a triangle, my exterior angle here, so I'm just going to call it 4. So this guy is equal to the sum of 2 and 3.
But how are those interior when they're outside?
So angles 1, 2, and 3 are interior. They're inside of your polygon.
In that.
And this
It
one.
looks like they're on the outside too.
A labels the vertex. So when I say angle A, I'm talking about the sides that make up that angle with the vertex A. You see what I mean? So A, B, C, D, E are just labeling the vertices, but we know that I can, like if this is C here, I can call this angle C because it's the only angle that's happening. Does that make sense? Okay, I see the confusion. Now, sides of the pentagon, you guys should have been fine with that. Diagonals of the pentagon. So again, you go from vertex to other vertices within your shape. We don't go adjacent because that's just the side of it. And so if I start off with vertex A, I would have AC, AD. Now as I move on to vertex B, again, I don't go adjacent, so I would have BD, BE, as I can see there. When I move on to vertex C, I don't go adjacent, so I'd have CA, but I've already represented that with AC, so you don't need to write it twice. That segment's already listed. And then CE. And then by the time I get to D, I've already done all the diagonals, and same with E. So we see that we have 6 diagonals there. So you don't have to repeat if it's already been labeled, because remember we can write this as CE or EC. And then our last piece here where it says name the pentagon, this is a very important thing with geometry, because a lot of times students will set up the problem wrong because they aren't familiar with how to name a polygon. So when we name any polygon, we want to go in either a clockwise or counterclockwise motion. It does not matter which letter you start with, and it does not matter which direction you go in, as long as you maintain that direction. So I just started with vertex A, and I went clockwise around, so A, B, C, D, E. You could have started with any letter. You could have started with D and gone counterclockwise and said D, C, E, A, E. What you don't want to do is just start and jump around, say A, C, E, D, B, because that gives us no indication as to the order of the letters. So our pentagon is pentagon A, B, C, D. Okay. Questions with this chart? Yes.
Wait, do you go, I know you go clockwise, but can you go farther?
Yep, you can go either direction, just as long as you're not jumping all around. Yes.
Can you just say A, B, C, D, E, or do you have to put like
If you don't have to draw a pentagon, we would say pentagon A, B, C, D, E. If we had just A, B, C, D, then that would indicate that that's a pentagon as well. Most likely it's going to tell you what you do.
Can you figure out like the diagonal based off the name? Like if you skip the second one,
Yeah.
and like just those ones overlap.
Yeah, exactly. So you would know that A, B, and A, E would be adjacent, so you'd have A, C, A, D. And then you'd have B, D, B, E, because you can't be adjacent. Yeah, very good. Other questions on this? Now, of course, your polygons are going to be different than your shoulder partner, probably. But go ahead and just show your shoulder partner, just swap papers real quick, and just double check that your shoulder partner did this right, that they labeled it properly. Convex versus concave is what it's called by its sides.
Can you do me a favor?
So you have give it
Oh. I was like, it's not
Take care of Now, I'm going to throw yours in this pile so you guys don't throw me gas on the desks.
What?
Lucy, what you doing with all of them?
Mommy, go ahead and put that away, my dear.
Good minus. Yeah. Here, you I know. I'm gonna ask if I can like do anything.
I'm gonna ask to call.
Okay, hand it back.
I'm gonna beg him for corrections.
And it's not like I got. There's no correction.
No, not Mr. Collins, George. I know I'm gonna.
Is there anyone that did not get the notes? Alright. Today's stuff is not super exciting because it's pretty basic, but at least it's a nice way to start off a Monday, right? You don't have to think too hard, but there's no Friday, so it's like it's already Tuesday.
Oh, and there's a half day on Thursday, so it's.
It's like the end of Tuesday.
Are we doing things on Thursday?
Yeah.
Oh yeah, it's 90 minutes anyway. That's why. What? Wait, isn't it Thursday? The 2 hour early?
It's a Black Day Thursday.
Oh.
Alright, so let's go take a look at our notes for today. Again, it's pretty basic, but that's alright. We have those every now and then. Alright, so our first theorem is the polygon angle sum theorem. And this says the sum of the measures of the interior angles. So note that it is our interior angles we're working with here. And what does sum indicate?
Addition.
Added. So if we add up all of our interior angles together, then we can use this formula to find what that total sum is. So it does not matter what type of polygon as long as it's convex. So again, we're focusing on convex polygons in our class. But it could be a regular polygon or a non-regular. It doesn't have to be regular. So our formula to find the total sum of those angles is 180 times n minus 2. This is what we had at the very bottom of our vocab sheet. What do you guys think n represents?
Number of sides.
Good. N is the number of sides. Which, if you think about it, the number of angles is also going to be the same as the number of sides for a convex polygon. Alright, so we use this formula, again, to find the sum of all of our interior angles.
Is the number of sides the number of interior sides or just like all the sides?
So a side is not specified as interior versus exterior. Side is just like the side of the polygon. We have interior angles.
Oh,
exterior angles. So it would be the same as the number of interior angles. Yeah, alright. So this first one says, what is the sum of the angles of a convex pentagon? How many sides does a pentagon have?
5.
Alright, so we just go 180 times 5 minus 2. Which is 180 times 3.
540.
Very good. 540. So 3 times 100 is 300. 3 times 80 is 240, right? 3 times 8 is 24. So add those together, get 540. So if I were to take any pentagon, as long as it's convex, again, here you'll notice convex starts to drop off because we are assuming it's convex and state otherwise. So if I were to take any pentagon, whether it's regular or not, and add up all the interior angles, they would add up to be 540. What's the sum of the interior angles of a triangle? Yeah, 180. So before we would take your angles, add them to be 180. Well, now we have to use this formula to first know how many degrees are inside of it. Alright, so go ahead and find the angles of a convex octagon and a convex 19gon. No calculators. If you have to do some math off to the side, that's fine. But no calculators. Find the sum of the angles.
I did it.
Well, hold on. You're close, but you're a bit off. Your numbers are close, but the final numbers are off.
Oh, we're done.
Go ahead and compare your answers with your shoulder partner real quick.
That's like one I got 1,080. And then yours did you do 18 times 17?
You get 1080.
Oh, yeah.
1080. That's 1,000.
How did you do it? It's like if you have 19, they're gonna have 19 times the 180.
No, like that. Dash times 180 is that 1,080.
Oh, I did something wrong.
Alright, how many degrees are there total inside of my octagon? 1080?
Yeah.
Awesome. How about the 17 guy? I mean the 19 guy.
3,060.
3,060. Do we agree with that?
Yeah.
I agree with that as well. Alright, questions on that? Now, as we go through, you'll notice that after a couple of days, you'll be able to quickly remember a pentagon is 540 degrees. You're not expected to memorize this because you can just as easily use the formula. But if a question asks about a pentagon and you know it's 540, you don't have to redo the math to show that to me. I understand and trust that some of you will catch this or memorize this just by process of using it. All right, Faisal, are you with me? Good. So remember, a regular convex polygon is both equilateral and equiangular. And if it's equiangular, that means that all my angles are the same. So let's say now, instead of asking what's the sum of the angles, what if they ask for just one particular angle? What is each angle of a regular pentagon? How would I find out what that is? Cameron?
Divide the total amount of angles by the number of sides.
Good. So I know for a pentagon, what's the total sum for a pentagon?
540.
540. So I can take 540, and if there's 5 sides, we know there's 5 interior angles, and just divide by 5, because they're all the same since it is a regular pentagon. And let's see, 5 goes into 500 once, 5 goes into 40, 5 goes into 48 times. So each interior angle is going to be 108 degrees because it's regular. If it wasn't regular, we don't have it in there. So in general, we can take that formula and divide by our number of sides. But note, again, this is only for regular polygons. And so that will give us 108. All right, go ahead and find what one angle is for our octagon and our 19gon. The 19gon does result in a fraction, so give me a mixed number fraction, like 5 and 2/3.
What's 1,000?
Wait, what?
And again, feel free to do long division off the side. That's what I did. See, right there, long multiplication, long division. Beautiful. Thank you. All right, so again, once you get your 2 answers, compare with your shoulder partner, see if you got the same thing.
Oh, that's not correct.
We expected to do a 19 find out what like a regular 19 got 19.
Well, you can do it by hand off the side. That's what I did too. Look, literally I have long division here. You can't forget that skill. That's one of those skills that's actually important for life.
Oh, wait. Oh, this doesn't work out. I don't know.
210 was good. Then you gotta put it back in.
116 6 times.
Ooh.
19 times 5.
It's going to be a mixed fraction.
Oh,
We like did that 600.
All right, so let's start off with the easier one. What was the angle of my regular octagon?
100.
Okay, I'm sorry, I was writing out what we did. 135? Give me a thumbs up if you agree with that. Awesome. Okay, what did we get for our
161.
161, and then how much did we have left over? 119. So we did the total sum. I don't know why.
Wait, what is in decimal?
I don't know. I'm not sure. So I leave it as a fraction, so I have the exact answer. So we took our total sum, the 3060, and divided by the number of sides, which is 19. And got 161 with a remainder of 1, so that's 161 and 1/19 degrees. For a very brief time. When you have to do Simon substitutions. Exactly. Alright, do we have questions on this first part? Alright, so how do we feel this first piece? Not too bad. It is some, you do have to do some math, some arithmetic. Alright, so now we have our polygon exterior angle, sum there. So the sum of the exterior angles is 360. There's no formula for this. It's just always going to be 360 degrees. Now again, we're dealing with convex polygon, and we're taking just one set of exterior angles because we know that for exterior angles, I can extend it out in both directions, right? We're only taking one set going around. But if I were to take this and draw in each of these and add my exterior angles together, I'm going to get 360 degrees regardless of how many sides I have. So what is the sum of the exterior angles of a pentagon? 360.
Oh, sorry. I wrote 360 there instead of the number one. I passed that.
What would be the sum of the exterior angles of a nonagon? 360. What's the sum of the exterior angles of a dodecagon? 360. How many sides is a dodecagon? 12.
Dodo.
Alright, so regardless of how many sides we have, as long as it's convex, 360 degrees. Now we can use this to help us find a single exterior angle. So now that we know a pentagon's exterior angles have to be 360, what is one exterior angle of a regular pentagon? 72 degrees. Now we have a couple of ways that we can do this. We can take 360 and divide by how many angles? 5. And I get 72 degrees. Or what else could I have done, which is probably what most of you guys do.
You can multiply by 2 and then divide it by 5.
Whoa.
You get 72. That's how you
Ah, because you're divided by 5. Gotcha. Okay.
60 by 6.
I first like multiply some things here.
Yeah.
Alright, what else could we do? Without even doing anything with my 360 degrees, if I already know my interior angle, how do I find my exterior angle?
Oh, it's the 180 opposite.
Okay. And what's the mathematical phrase we use for that?
Supplementary.
Thank you, supplementary. So our interior and exterior angles are supplementary. And so if I already have found my interior, I can just do 180 minus that, right, Jalen? Good, put that away, please. So again, we can use this to solve for an exterior angle. Jalen, put it away. Thank you. Or we could go ahead and do the interior angle, do the supplement. Questions with that? Okay. So now we have, given a regular hexagon, you're going to do the same similar thing. So go ahead and do this next example here with a hexagon. Find the interior angle and an exterior angle.
It is 6.
And hopefully the smart board will come back.
So if you're trying to find the interior angle, can you just divide it into 360 and then take out the exterior angle? So that's like that's going to be the long division enough.
What she just said. So what she was
That was
saying
a
was
lot.
that to get an exterior, we did 360 divided by the number of sides. So she's saying instead of doing the interior angle formula of the 180 times 7 minus 2, she's saying first find your exterior. So we do 360 divided by 6. Get your exterior, and we know those are supplementary. So we do so. You're not required to do one. Alright, what did we get for our interior angle of the hexagon? 120. And then how about our exterior angle? 60. So again, the interior angle, we know the total sum of interior is 180 times z minus 2. Since it's a regular hexagon, just trying to underline there. Since it's a regular hexagon, I can just divide by the number of sides to get this. Exterior angle, the total sum of exterior angles is 360. To get one of them, since it's regular, I can just divide by the number of sides. Now this brought up a good point. She said, could we start off by finding the exterior angle? So we just do 360 divided by 6. And then do the supplement of that to get your interior? Certainly. You're not required to start off with one and go to the other, whichever method you do. Alright, so now our next example here, it says find all 5 angles of the following polygon. First of all, what type of polygon do I have here? A pentagon. We see there's 5 angles, or they told us 5 angles, but also we see the 5 sides. So I know that this is a pentagon, so my number of sides would be 5. Now, is this a regular pentagon? No, they did not give that to us, and we cannot make that assumption. So I do not know that these are the same, and in fact, we'll find that they are not the same at all. So how do I go about finding my angles? What do you guys think I should do? Jalen?
I don't want to see the measure all the
Yeah. If it was a triangle, we'd take all three and add them up and set them equal to 180. So same idea, it's just not on the pentagon. So we need to figure out what's the total sum of the interior angles of a pentagon, and then same idea there. So I'm going to go ahead and add up my angles. Instead of writing them all, I'm going to do a couple chunks at a time. So I'd get, let's see, 9x minus 30 plus, we can do each of these. So let's see, 6x plus 1x would be 7x plus 90 equals, and how do I find the total sum again? It's 540, yeah. And if you forgot, again, 180 times n minus 2 gives me my total sum, and if you look from above, that's just 540. But that's where our 540 came from. Okay, so then we can just go ahead and solve. I'm going to think about this.
Wait, why are you just doing
Up here, we already did the wood.
Am I just doing that?
two angles? Right?
Oh no, I was adding them together as I wrote out my equation.
Oh.
So I didn't have such a long string. Which you can write them out individually. I was just trying to save space. So again, our 540 came from doing that 180 times n minus 2 for n is 5. Alright, go ahead and solve for x, see what you get. And then notice it says find all 5 angles. So once you've gotten x, go ahead and find what each of those angles are. Alright, what did we get for our x value? 30. Beautiful. And then go ahead and carry on to find what your angle measures actually are. And you can actually just go and write them on the picture yourself. Once you think you have it, go and check with your shoulder partner. Alright, what do we get for angle B? 114. 114. So 114 degrees for B. How about C? 126. D? And as you can see, once again, the pictures are not drawn to scale. Alright, how about E? 110. And finally A? 100. Now, notice something different that we can now encounter. With triangles, how many obtuse angles could I have in a triangle? Just one, right? Notice, since our total measure is 540, obviously we can have many more than just one obtuse angle. So don't be concerned if for something more than a triangle you do have more than one obtuse angle. Alright, questions with this? Okay. So go and flip your paper over. And on the back side here, it says find the missing angle measures. These are kind of typical types of problems that deal with our concepts for today. So notice they don't tell you what type of shape it is, but I trust you guys can count sides to figure that out. And so you're going to use the information given to you along with the theorems that we learned today to solve for these unknown values. Notice it says find the missing angle measures, so don't stop at just finding that variable. Find the actual measures themselves. So on number 4 here, I do want to make sure we all understand that x plus 50 is for this angle as well as these angles here. Okay, so make sure you don't neglect that one that is actually sitting there. Alright, so what you're going to do is go ahead and scoot your desk together with your shoulder partner, and you're going to work on this back side, and then we're going to come back together and go over the Brianna.
So we don't need a pair.
If you want to move
It's a parallelogram. Alright, so then.
Alright, so let's go ahead and take a look at our answers we have so far. Do we agree with number 1? So we've got x is 40, 100, 80, 180. This is correct. Do we have questions on this? Questions on that one? Alright, number 2. I agree with number 2. Do we have questions on number 2? Amani, did you have questions? You're good?
Are those not right angles for the first one?
No, nothing was given to us to know that they are right angles. Paige, did you have a question?
We got 126.
For y?
My dad lived in Japan for
So you're set up for number 2. William, calm down. Our setup for number 2, I have y plus y, or 2y. And then I have 2y minus 20, 1, 2, 3, 4 times.
Oh, we didn't.
And then it's a hexagon,
Yes.
Yeah.
so it adds up to be 17.
Oh, we did 6Y.
Ah.
Yeah.
Well, you will have 6y minus 80.
Oh,
Because you remember me stripping
no,
them.
we have minus 40.
Ah. So you lost a couple points.
Yeah.
Okay. 3, I agree, and 4, I agree. Do we have questions on either of those? All right.
I have a question.
Yes.
I have
I forgot the extra 40 on the
Which one?
two.
What about?
76.
So I did it.
Okay, so this is the setup. Questions on that setup?
Wait. No.
Okay, so then if you have the same setup, your math just went wrong somewhere.
I see.
Okay. All right, so 5, 6, and 7. I agree with 5. Is that a 2 or a 1? If it's a 1, I agree.
Oh, we were right.
133. And 7, I agree as well. Do we have questions on 5, 6, or 7? Okay. And then 8 looks good. And 9 also looks good. Questions on these 3? Okay. And then let's go take a look at the very last one. No, A is going to be 108, so this is a pentagon. Is that what we have there?
Yeah.
So pentagon, and the total sum of a pentagon is 540. Divide by 5 gets me that 108. And then B is going to be supplementary to that, so we go supplement with that. Alright, so for our bottom one, it says if the measure of an exterior angle of a regular polygon is 45, find the measure of an interior angle, then find the number of sides. You did not have to do that and do it in that order. If you didn't want to, you could have found the number of sides first. But they tell us that an exterior angle is 45 degrees. And we didn't know how many sides it has. Alright, so if I know that my exterior angle is 45, my equation to find a single exterior angle would be 360. Because it's regular, I can just divide by the number of sides. So I can use that equation to solve for n. Or you could have gone ahead and it says find the measure of an interior angle. So you can go through. Now that if we already know our exterior angle, what's the interior going to be? The supplement of it. So what's the supplement of 45? 135. Good, 135. So you could have used that equation. We know that our equation for an interior angle would be 180 times n minus 2 gives me the total sum. And we would divide by the number of sides to get one single point. This way is probably going to be a lot easier to solve for n than the other way, but you can use either method. So what did we get? What's our number of sides? Good, it's an aunt.
We also did the work on the dots earlier.
Alright, questions with that one? Okay. So for our remaining time, you're going to get the chance to work on your homework, and those of you that did not do add-ons will do those. So go ahead and scoot your desks back to where they were.